Hello, now it's an official. Hello. Don't come back on Monday. Yeah, Monday is a holiday. Today my goal is to spend to 10 more minutes to finish this topic and move on to the last one. Technically, I only have to do this part because it's mostly about demonstrations, but I like it. It's fun. So, less than 40 seconds left. I'm going to make a fountain. Be careful. But first, in 15, 14, 13 Mississippis, I'll see what you think about it. Can you hear me? On the back? Yeah. But I won't tell, yeah? All right, so what's wrong with this? Everyone who pressed 4 should have a suggestion ready. So, anyone? Yes?
Well, both the ends are open, so the pressure would be the atmospheric pressure in both, so it would push it out.
So, both ends are open. It means without additional pump, the water can't go higher than the original height. It only can go as high as the another level. You remember I had a U-shaped tube here, and the level has to be always the same. Doesn't matter if one of the parts of the tube cut, still water can't go any higher. And if we want to calculate, we just need to know this height. The speed of this surface is practically 0, done. And a similar situation is called not a fountain, but a siphon. So don't press anything yet. You don't know the question. All you can read are answers. Now the question. So one end is in this bucket. Now if I slowly start here. My favorite camera. I don't want you to think I'm cheating on, no. It's pure physics. You can see what I see, hopefully. Yep. So this end is here at the bottom of this bucket, and now I start slowly moving this end down. Yeah. So my question is, when this end will be lower than this red mark, will its water start moving? 1 for yes, 2 for no. Okay? I'm going to do this slowly. So eventually this goes below this mark. And my question is, will water start moving? 1 for yes. 2 for no. And if you're late, this is the personal response where ID, and now I start my timer, and I even get rid of some seconds, and now I'm switching back to this camera, and now I'm starting doing this. So everyone has to press already something. Lower, lower. What did you press? Okay. Lower, lower, lower. Did any press one? Anyone press one? Pressed one? I will find out very soon. Of course, nothing should, well, again, first you have to make it move, and then it will keep moving. So how can we make it move? What do we have to do? Some men should know. Yep. You have to apply a pressure difference. That's a scientific term. That's it. This is how your neighbor was stealing gasoline from you. And this is your fountain. And of course, it can't go any higher than the original level. Now it stops. What do we have to do to make a fountain like this? We have to attach a pump. We have to keep adding pressure. And well, if you have a pump, you can build up a fountain at home using it. Let's see the answers. What is 3? I can't think. I don't like physics. I'm tired. Everybody, you know. All right, so read the blue sentence, because I'm going to ask you this question. Think about it. This number is huge. The atmospheric pressure is huge. Yeah. So if you take 1 square meter of surface, which is about this big, this is 1 square meter of surface. An average person has a skin area close to that number. So everybody experiences 100,000 newtons of force pressing. See? So the question is, why are we still alive? Think about it. Now, to demonstrate that atmospheric pressure is indeed really, really strong, I've got a couple of more things to show. Number 1, a can getting crumbled. The sole reason for that is this pump is sucking out the air, and the more vacuum is inside, the more pressure it experiences outside. It actually broke right here. So I can't make any more vacuum in it. There is a hole. So that's how strong it was. And imagine that the same would be happening to us. Won't be good, right? But exactly the same pressure is acting on us from above. Now, I need another person to press a button. 100 years ago, when pumping mechanism was developed and enhanced. A similar experiment for many people looked like a miracle. Magdeburg's hemispheres, well, I do have those, not from Magdeburg, of course. Basically, what I want to do is just suck out some air, and I could have used the pump. I don't want to, because even my lungs enough. Maybe not today. One more time. Well, yeah, that's it. So, what is the volume of human lungs? 2-3 liters? And just taking out this very small volume is enough to make the pressure difference strong enough to prevent this from falling down. And of course, if I use the pump, well, it's not so strong, I can actually break it. But if I use the pump, even, well, a strong person could not break it, but in actuality, you don't need it. You can buy these suction cups. These are contemporary Magdeburg hemispheres. Who's the strongest person here? You? No? All right. Pass it around. You can just pass around. 1665, still using. Yeah. So, and my last experiment. I want to show a slide of what's happening, what's going to be happening. This device has a name, air cannon. It's a cannon. It shoots. And the speed of the ball leaving the cannon is actually practically equal to speed of sound. So this device can be dangerous. And all it uses is the atmospheric pressure. So all I need is to, well, first of all, I need to put a ping pong ball in it. Why is it blue? I use the blue marker in it. It's for better visibility. Now we need to seal the ends. So let's hope. Sometimes it happens like, I don't know, 1 out of 3, 1 out of 4 times. Sometimes a piece of tape getting stuck to the ball and prevents it from, because of the internal friction, from flying out. But, come on. You still think about that question? Why we're still alive? Well, I'm going to switch, and I need a target. Because in previous years, actually, I might be able to show it to you. Previously, people who were shooting at walls, and here you see a spot, white spot. See? I don't want to do that, especially on the record. So my target going to be just a box. And just in case it wouldn't fly away a heavy weight. We'll see. It's physics. You can't be always sure that something unpredictable will happen. But if nothing unpredictable will happen, so all I have to do is make a vacuum. This is actually not a commercial pump. It can't make a very, very deep vacuum. I need someone to count Mississippis. I need 120 Mississippis. Oh, you can hear the sound changes. So it's harder and harder for this pump. How many Mississippis? Okay, so now I use a contemporary counter. This is an explosion. What do we know about explosions? They're very loud. So everybody who close enough for fourth, fifth row should cover the ears just in case. It's too late for me. I've done it so many times. I can promise it's going to be loud. I can't guarantee the ball will fly out. Again, 1 time out of 3 it doesn't. So 31 should be close enough. All I have to do now is just pinch this to let the air rush in and push on the ball. This is that third time when it didn't work. I wonder why. It's stuck right here. You can see it. Last week it didn't work for several times as well. Let's come out. Oh. The piece of tape. I can't even take it out. Now we'll have to shoot it again and again and again until it works. Where is it? Here. Yeah, there's a piece of tape right here at the very end. Bad luck today. See? Well, let's try one more time. It's very rare when it doesn't work 2 times in a row. Same ball. I always can cut it out from the lecture, but I won't. So we're not going to lose more than 2 more minutes, so it's not a big deal. Now, maybe my ceiling wasn't good. This is what I use to cover the sticky part of the tape, trying to prevent it from sticking to the ball. Well, open, turn, start. And I want to use this time to discuss next slide. So we're not losing any time. This is the last slide related to the atmospheric pressure. Remember, the Bernoulli's equation tells us faster flow, lower pressure. Slower flow, higher pressure. Why? It's actually very, oops, it aims right at me. It's actually very easy to explain. What is a pressure? Pressure is the result of many encounters, hittings. Yeah. Every molecule of air or water travels and hits a wall, and if 10 molecules per second hit every square meter, that's one certain pressure. But if 100 molecules per second hit every square meter, that's a higher pressure. So all depends on how many molecules hit a square meter per second. And if liquid flows slowly, so many molecules can hit. But if the liquid flows fast, that's it. So the number of molecules which hit the same area decreases. And that decreases the pressure. So every phenomenon in physics, of course, has an algebraical explanation. We call it an equation, a law, but also a very simple model which describes it. Well, let's check my luck second time. Close your ears. It wasn't even loud. It's Friday. Nobody wants to work on Friday, especially before a long weekend. No luck today. Moving on. I might try it again sometime later, but not today. I can't waste too much time on this. Not everything which we want to work always works. That's one of many lessons of this course. Do not read this slide. So the next topic, well, the large topic is all about temperature and thermal properties of matter. How do we measure temperature? We use this. A thermometer. Well, not only this, we have digital thermometers, many kinds of, but the simplest one, it's basically like a thin, tiny graduated cylinder with some liquid inside. And normally, rest of the world uses Celsius to measure temperature, but some people on relatively small Earth area, Britain and USA, they use Fahrenheit scale, but physicists all over the world, they use a different scale, which uses kelvins. This scale has a special name. We call it the absolute scale temperature. So to develop a scale, what can we do? Anybody can develop a scale, temperature scale. It's very simple. Professor Celsius, he took a graduated cylinder, put it into first into iced water, draw a mark, wrote 0. Then put it into boiled water, draw a mark, wrote 100, and divided everything into 100 equal spaces. That's it. Professor Fahrenheit did something more complicated. You can Google. Professor Kelvin didn't do anything. It's just a name. The absolute temperature scale is defined differently, completely differently. We'll talk about it next week. For now, all we need to know is that all three scales are related. Here we can see conversion factors between Celsius and Fahrenheit. Here we can see conversion factor between kelvins and Celsius. One of the reasons this scale has a name absolute, because it has no negative temperatures. So the absolute 0, that's the minimum temperature in Kelvin can be reached in the universe. Like speed of light is the maximum speed. Absolute 0 is the lowest temperature. Fahrenheit, Celsius, those temperature scales have negative temperatures, but this hasn't. And another good thing about using Kelvin or Celsius, change is the same using any scale. If you use Fahrenheit, change in temperature will be different from change in temperature in Celsius or in Kelvin. So that's another reason why in physics people don't use Fahrenheit. If we want to change a temperature of an object, we must bring it into a contact with another object. Otherwise, it's going to be impossible to do. So we must have a hot, warm object, and we can use it to warm up a different. We can bring into the contact directly or use radiation, doesn't matter. Like the sun doesn't touch the earth, which is good, but it provides radiation, and that gives us, well, energy to live. And the amount of energy we have to transport to warm up something, to heat up something, or to melt something, or to freeze up something, that amount of energy has a name, heat, or heat energy, but shortly heat, because it's a form of energy. The unit of heat is a joule. But very often in the practical world, instead of joules, people use calories. Again, there is a conversion factor. 1 calorie is about 4 joules. So 2,000 calories is about 8,000, well, 9,000 joules. And these equations, complete new equations, technically, we need to learn for solving many, many future problems. This is the amount of heat an object absorbs when it heats up, or releases when it cools down. If final temperature of an object is higher than the initial, the heat is positive, that object absorbs the energy. But if final temperature is lower than initial, this difference is negative. The amount of heat assigned to that object is negative. That means object giving away, releasing that energy. And of course, for different objects, the amount of heat required to make 1 degree temperature change is different. So this coefficient tells us how much heat has to be spent to change the temperature by 1 degree. By 1 degree. And that coefficient, of course, has a name, heat capacity. Now, if we want to melt something or freeze, that's what we call phase change. Yeah, we know 3 major phases: gases, liquids, and solids. So if we want to make a phase transition, of course we have to spend some energy on that. And of course that amount relates to how much matter has to be changed, melted or frozen up. And this coefficient depends on the material, on the internal properties of that matter. So the amount of heat we have to spend to melt 1 kilogram of something, that's what it is. And it has a name, latent heat. Well, it could have been latent heat of evaporation, or latent heat of melting, latent heat of fusion. Doesn't matter. Still, everybody calls it latent heat of something. And that's what it is. If instead of melting you want to freeze it up, in that case, that system has to release, give away the energy. So in that case, that amount of heat assigned to that process should be negative. So the difference between that equation and this equation is important. Here, we automatically have positive value for absorbing energy and negative for releasing. They're subtracting numbers. Large number minus small number, positive. Small number minus large number, negative. Here, we have to remember what we should write in front of this coefficient, a plus or a minus. So we have to understand what's happening. If the system should absorb energy, we have to write a plus. But if that system should release, give away energy, we have to write a minus. It's up to us. Now, the capital C represents a property of an object. So how much of that object is and what it's made of. So if we take that capital C, the heat capacity, and divide by the mass of the object, this variable now only related to that material it's made of. So this coefficient has name specific heat of that substance, specific heat of water, specific heat of lead, specific heat of ice. We can't say heat capacity of ice. No, we can say heat capacity of ice cube, yeah, because heat capacity is related to an object. But specific heat of ice, that sounds right. And of course, normally this is how everybody writes the equation for the heat related to the temperature change. It's too soon. We're not done yet. So, specific heat this is an official definition. A specific heat of a substance is equal to the amount of energy which we need to supply to 1 kilogram of that substance to warm it up by 1 degree. So if everything is equal to 1 kilogram, 1 degree, that's what people measure. And of course it has been measured for all substances, for all materials. You can Google aluminum, copper, gold, water, what's the difference? Well, the chemical structure is the same, H2O, but the phase is different. It could have been gas, vapor, water, what we call liquid water, yeah, and ice, what we call solid water. And depending on the phase, again, specific heat differs, so we just have to read carefully. If it says water and it's assumed solid water, ice, yeah, we have to use this number. If it says water and we know it's liquid, regular water, we have to use that number. That's it. So this slide completes everything I just have said. Nothing new, just one slide for everything. You see? Depending on what is happening, we have to choose what equation do we need to use for that particular heat. Freezing, yeah. We take a cup of water, place it in the freezer, water giving away energy. Minus. We take a piece of ice out of the freezer, it starts melting eventually. So that piece of ice absorbing energy plus. And another fact, the heat exchange happens every time when two objects with different temperature are in contact. If you take a tea kettle and place it on a stove, stove provides energy to water, water warm it up, eventually might start boiling. But this is what we call open system. Water in a kettle is in a contact with the heat plate, which is in a contact with the energy source, electric power. But if we take styrofoam container and we put something inside, water, ice, solid things, different temperature, in that case we can make a valid assumption that this container thermally isolates what's happening inside from the outside. That's what we call the insulated or isolated system. In this situation, if we have several objects into the contact, thermal contact, but not communicating with the outside, well, the law of conservation of energy tells us the total amount of energy inside this system can't change because there is no connection with the outside. Only outside might take or add energy. If that's not happening, total amount of energy inside of the whole system has to be the same, which means the amount of heat objects absorb should be balanced out with the amount of heat some other objects release. That's it. That's the only way to keep the energy, total energy, the same. And as we know, if an object absorbs energy, heat related to this process is positive. But if an object is releasing energy, the actual value of heat assigned to this process is negative. So we always can write that for any amount of released energy, it should be equal to its magnitude times -1. So that's what it is. Or the magnitude of the energy released is equal to -1 times the actual value. That's pure math. So if we use this fact, we can rewrite the law of conservation of energy differently. This is also the law of conservation of energy. But some of these terms are positive. They're related to absorption of energy. And some other terms in this equation are negative. But if we add them up all together, there is no change. So everything has to be equal to 0. This equation has a name. When heat is being balanced, the equation is called, any suggestions? Balancing torques, torque balance equation, balancing forces, force balance equation, balancing heat, heat balance equation, exactly, that's the name for this equation. And that's it. That completes all the theory. So I want to ask you this question. That should be my last question for today. So I'm going to give you, like, I don't know, 5 seconds. So questions are, well, your answers, your choices are related to the statement above. If you take an ice cube right out of the freezer and you place it on a heat plate, working heat plate, it immediately starts melting. That's a statement. As any statement, it's either wrong or right. That's it. No other choices. And technically, you don't have to know this. It's just your life experience, your intuition, and this statement is wrong. We don't have to know that. We have to use our experiments, and experiments tell us. So now, now you know that there is a certain amount of heat related to temperature change, but the phase change is not the temperature change. Temperature change happens when temperature changes. Phase change happens when phase changes. And phase change happens when temperature stays the same at specific phase change temperature, critical temperature. For every phase change, there is a temperature has been measured, tabulated, when that phase change might happen. For example, what is the temperature for the change we call melting? At what temperature ice starts melting or water starts freezing? Well, depending on scale, you can choose any scale you like and say either 0 Celsius or 32 Fahrenheit or 273 Kelvin, doesn't matter, it's the same temperature, we just measure differently. But if ice is not at 0 Celsius, it can't start melting. It has to first warm up to 0. And then it starts melting. And until ice doesn't melt completely, temperature remains to be equal to 0. So these equations, this equation and the equation with temperature, cannot be applied to the same process. It's either or. Either temperature changes and you write Q equals C delta T, or phase changes and you write one of these. Never together. So how does it look like? Well, graphical representation, normally very helpful. To demonstrate what might be happening. The only problem is that this is a standard variable for time. And this is the standard variable for temperature. So we just have to remember time, temperature. So let's start from, well, if it's a piece of ice, so we take it and let's say it's -5 Celsius. It can't start melting until it reaches the phase transition temperature. Then it melts, and it takes a certain time. But until it melts completely, temperature doesn't change. And then, of course, there is no ice anymore. What's left? That's what we used to call just a water. This is a mixture. Yeah. So it warming up, it warming up, it warming up, eventually it reaching 100 Celsius or 212 Fahrenheit. What's happening now? Now it's boiling, evaporation. This is another process which takes time, but until water completely gets evaporated, temperature doesn't change anymore. So again, this is a mix of water and vapor. And only after that, when we have just gas, temperature starts rising again. Gas. So, of course, for each process like that, Q is positive. So, this. But let's say you start from a gas and you're taking away energy. So now the system, the gas, is losing energy. In that case, we're gonna go through exactly the same stages, but backwards. Yeah. Gas, first cooling down, same equation, automatically works. But the phase transition now for condensing, well, should have a minus in front of it. Then again, we can use the same equation for water cooling down to 0. Water can't be colder than 0. There is no water below 0. It's ice below 0, right? But to transfer water into ice, we have to take away more energy, so freezing this equation. So for all red arrows, all amount of heat is negative. So, a specific problem. A bullet travels. If we know its speed, we can calculate its kinetic energy. So its kinetic energy equals mass speed squared divided by 2, 0.01 kilograms, 100 joules. It's actually 50 joules, right? Okay. 5OJ. What's happening? It stops. It hits the target. Well, first of all, why does it stop? Friction acts on it. Friction makes it stop. It travels through the target a little, and what is happening to the energy? It's getting transferred to the heat completely. So the amount of heat released by this bullet will be equal to the amount of heat absorbed by this target. Of course, will be equal to the same magnitude, 50 joules. That's a law of conservation of energy. All right, that's all we need to know. The rest is what? Well, strictly speaking, depending on the parameters, two things might happen. So, number one, so the temperature of the bullet might rise, and that's it. But number two, if the energy released by the bullet is, well, it's actually released by the bullet and absorbed by the bullet, we neglect any loss to it. So the bullet was flying, and that energy now gets inside the bullet to make it warm or melt. Melting temperature, 3 to 7.5. If the final temperature is below that, that's it, it stops. But if the energy is more than we needed, in that case, a part of the bullet or the whole bullet might melt. All right. Don't come back on Monday. I'll see you on Wednesday, labs on Tuesday, downstairs. Please don't forget to sign in or sign out. Yes. I'll take care of it. You just have to open it. Yeah, let's do stuff to start. Yeah. Kind of mistake. All right. flying out with 300 meters per second.
Oh, no, that's pretty bad.
No, it's very dangerous because I'll show you. There is a spot on the wall.
Oh, like that?
Yeah.
The white one?
That's exactly what there's one. So, if everything works fine, it actually makes a huge hole in it. But it didn't work quite for me. It did work last week or last week. So, I'm afraid maybe the pump is over there.
Yeah, I'm not.
Yeah, we do. We need to check it. Only 90 seconds should be sufficient. Alright, so let's see. How cover you use?
Oh, wow, that went.
That's what I'm talking about.
That's true.
See
I
it?
didn't even see it exit.
See
Like
it?
that.
See it?
Oh. That was pretty strong. Wait, did it hit the wall? No, it just went. It hit a couple of things.
Of course, it travels with the speed of the sound. Of course, you can see it. See it? Cool, yeah. Okay.
I didn't even see it like exit. I just like I wasn't ready. I just heard it exit and it's like true that. It's pretty like it's very it was really fast.
I did record it.
You did? You did?
No, I didn't.
Let's do it again.
Something is wrong today.
What ball?
All right. I'm going to give it another try on Monday's holiday.
All right.
So you're my witness.
Here the tape's over. Yes, sir.
Yeah. Problem is, you never know why exactly it didn't work. What to fix. Maybe you're right, maybe I have a meeting. Next time, it's not gonna work.